Okay, so we're going to go ahead and talk about how we can use our models that we built earlier to get some basic conformational analysis done, right? So we can actually look at the relative configurations of the atoms, on the left side versus the right side of the molecule. And we're again using our 111 trichloroethane as an example in the sort of the model where we have all the atoms represented as spheres, okay, including that one there, including the carbon, or the one where we're using this clicked together pair of sort of V-shaped groups to give us our tetrahedral carbon center. Okay, so the first thing we're going to do is look at this particular molecule here, in this particular conformation. We can look at it from this sort of perspective, right? This is our wedge dash one. The carbon-carbon bond is sort of along the plane of the screen, okay? And so we've got our CH bond here, and this CCl bond up here. Both of those are actually along the plane of the screen, or along the plane of the page. That CH bond there is coming towards you at the screen. That CCl bond there is going towards you, and that CH bond's going back, and that CH bond's going back. So if we think about that, right, we can represent this in terms of the sort of wedge dash type conformation. We can represent it as a eclipse conformation because the position of the CH bond, right, is the same as the relative configuration, or lines up with the configuration of the CCl bond. Okay, now we can go ahead and rotate that molecule, okay, 90 degrees, and now look down the carbon-carbon bond. Okay, so we can look down that carbon-carbon bond, and we can see either that if we look down the carbon-carbon bond with the hydrogens at the front, or the one with the hydrogens on the back. But regardless, we're going to see that we have the three, hydrogens here, basically lined up with the three chlorines on the back carbon in this case. Same is true if we go the other way around. We can see that the three CCl bonds line up with the orientation of the CH bonds, right? They are eclipsing each other. So if we do that in the context of a Newman projection, okay, we can go ahead and see that that looks a bit like this here, okay? The CH bonds are eclipsing the CCl bonds. Okay, so how does this work in the other type of model, okay? So this here looks pretty similar, okay? We're again in a eclipse conformation. If we're in the wedge dash type structure, see this CH bond and that CCl bond line up on the plane of the screen. The C bond, the carbon-carbon bonds along the plane of the screen. That CCl bond's coming towards you. That one's going away from you. This one's coming towards you. And that one there is going away from you. So again, whether in this conformation or if we rotate it to put the carbons lining up with each other in sort of a Newman type fashion, okay, we again see that we're in a eclipse conformation. We can see that this CH bond lines up with this CCl bond. So overall, we get very similar information from both of these models here. Okay, we can see that in both cases, we get very comparable type information. Okay, and we can represent it in the Newman form with the eclipsed CH bonds eclipsing the CCl bonds in the back. Okay, so how do we go ahead and do our conformational analysis? So the nice thing is that both models allow you to rotate around the carbon-carbon single bond. So this one here, I can rotate it 60 degrees, and that'll put me in a staggered type conformation. We've gone from an eclipse one to a staggered one. We see the three CH bonds at the front are at 60 degrees to the three CCl bonds at the back. Okay, we can get very similar type information if we take our original model with sort of the solid sphere type approach, rotate, say, the back carbon by 60 degrees, It's always a good idea to either rotate one or the other, but not both at the same time. So rotate the back carbon by 60 degrees. And again, we enter a staggered conformation where there's a 60-degree angle between any of the CH bonds and any of the CCl bonds. We can represent this in the Newman type form, or we can represent that in the wedge dash type form. Okay, if we're doing the wedge dash type form, that CH bond and this CCl bond are along the plane of the screen, as is the carbon-carbon bond. That CCl bond and that CH bond coming towards you, and this one up here in terms of the CCl bonds, and that CH bond are coming out away from you, away from the screen. We can get a very similar type representation from this model here. Again, we have the CH bond, the carbon-carbon bond, and the CCl bond all along the plane of the screen. That CCl bond and that CH bond are coming towards you, and this CCl bond and that CH bond are all going away from you or behind the screen. Okay, and so we can actually represent those, okay, in our wedge dash type form, okay, in the staggered type configuration. So that's what we represent through this molecule here, or that representation there. They both represent a wedge dash type conformation with a set of CH bonds and a CCl bond flat along the screen. The CH bonds coming towards you, CH bonds going away from you, CCl bonds coming towards you, CCl bonds going away from you. Same in this type of representation. Or we can go ahead and rotate by 90 degrees, looking down the pair of carbon-carbon bonds, go into the Newman type configuration, the staggered. I have a Newman type projection with the staggered conformation. And again, we see that the pairs of CH bonds are at 60 degrees to the CCl bonds. They're no longer eclipsing each other. Hopefully that was a useful way of, representing different types of molecules and being able to use your model kit to get, conformational analysis. We can apply the same ideas to bigger molecules or other types of structures.